Okay, so let's talk about systems of nonlinear equations and how we can extend the idea in the Newton-Raphson algorithm. So uh, suppose we have basically two nonlinear equations. So for simplicity, I will just use two equations and two unknowns case, but the same, whatever we do here can be extended to the d-dimensional case. No problem with that. So what we will do here is basically we are trying to solve this system of equations, which can be a nonlinear system of equations, and we will just start by taking the first order Taylor approximation in both of these functions. Okay, so similar to what we did in the one-dimensional case, we will consider the Taylor expansion, a first order expansion, and since we have multi dimensions, like it can be two or more, we will have these partial derivatives this time. And just like we did, remember that if we write the Taylor expansion as we did last time, so we have this x minus x0, f prime evaluated at x0, and we have these other terms. Let me write this as big O x minus x0 squared. And notice that actually this x was considered as substituted as x plus h, and instead of this x0 we are just considering x. So when we take the difference of x minus x0, so we have this h, and this is h squared. And by the definition of being the root, so our purpose by writing x plus h was to get closer to the root of this problem r, right? So we want to solve, and we want to set this left hand side of the equation equals to 0, and we can solve the right hand side with respect to this h. So the same thing applies here. You can see that we set the left hand side equal to 0 because we are looking for the root of this problem. So okay, so once we get here, you can see that we can represent this system in matrix notation, and that's not very difficult to do. All you need to do is collect all these coefficients, and your unknowns here are these h1 and h2 terms. Okay, so if you collect these coefficients and you have this multiplication with the vector of unknowns, and the right hand side becomes minus of these function values f1 and f2. So we call this matrix of partial derivatives as the Jacobian matrix denoted by J. You might have seen this matrix in calculus. Even if you haven't, that's not a very important thing for us, I mean, to remember the name. But basically, we can solve this system with respect to this h, and that can be calculated as J inverse times this vector f1 and f2. So basically, if we apply this recursively, and notice that this is our vector x, and this part is basically h. So every time I calculate this h and add to the previous x values, I get closer to the root of this system. Okay? And let's see an example. So in our example here, we have three nonlinear equations, and we have actually x1, x2, and x3. So we have three unknowns and three equations. Okay, so how we can solve this system? So first of all, we can actually represent this system by collecting everything on one side of the equation. So what you need to do is put everything on one side, and the right hand side I would like to have zeros, and then you can have this x1, x2, x3 plus x2 square minus x1 square minus 2 equal to 0, and then the last equation, sorry, this should be x1, so you have plus x3 minus e to the power, so this should be x2, there's a some typo here, and then minus 3 equals to 0. Okay, so now we can calculate our Jacobian matrix, and that's not very difficult. So for example, you start with the first function. This is your f1, this is your f2 here, and this is your f3. So for each, since you have 3 coordinates, you need to calculate 3 partial derivatives for each function here. Okay, so for example, if I take the partial derivative of the first function with respect to x1, I get this x2 term, that's all. And then if I take the partial derivative again of the first function with respect to x2, I get x1. And finally, if I differentiate with respect to x3, what I get is minus 2 times x3, right? So you can do these one by one, and you can see that this is x2, x1, and minus 2 times x3. And you can write down the partial derivatives of the second equation, and finally for the third equation. So once you calculate the Jacobian matrix, the rest is going to be easier. So you simply start with some initial x0 value that can be an educated guess. And of course you want to, if you start with an initial value that is relatively close to the root of the problem, then it will of course speed up the convergence. But you can try and do some trial and errors, and you can always change your initial conditions. That's okay. And you can see that I start with some initial x of k, and starting with the k equal to 0. And we know how to calculate this term here. So basically at each iteration, I can start with the 0, and this is going to be my initial guess. So that's going to give me x1. And I can calculate this vector, and what I have written is basically the value of these vectors. So at the initial time step or initial iteration, this is our initial condition, and then we write what is the value of x1 using this equation, and you can calculate these on your computer or using a calculator. And you can notice something here. I mean, if we do the calculations in our MATLAB, which we can do easily, after a few iterations, you will notice that the value of this x vector does not change anymore, at least within the, let's say, 5 digits after 0. So this means that basically we have achieved convergence, and if you are satisfied with these 5 digits after the 0 decimal, then you can stop your algorithm, because there is no need to repeat more iterations unless you are getting something new or a difference in the x values. So this shows that actually within a few iterations, the Newton-Raphson algorithm actually converges to the solution, the root of this nonlinear system, relatively fast. So later on we will do some examples in MATLAB. So let's stop here.